The moment you set foot on Mercury, you are already dying. Not in the slow, poetic sense that we are all moving towards some eventual end, in the immediate, clinical, irreversible sense. Your suit is failing, your cells are being shredded, the ground beneath you is either hot enough to melt lead or cold enough to freeze your oxygen supply solid, depending on which way you're facing. And the star responsible for all of it hangs in a black, airless sky, 3 times larger than it appears from Earth, silent, indifferent, and absolutely lethal. This is not science fiction. This is the surface of a real planet in our own solar system. A world we have mapped, studied, and sent spacecraft to orbit, and it would kill a human being faster than almost any other environment in the known universe. Mercury is the smallest of the 8 planets and the closest to the Sun, orbiting at an average distance of about 77 million kilometers from our star at its nearest point. For comparison, Earth sits at roughly 150 million kilometers. That doesn't sound like a catastrophic difference, but proximity to the Sun is only one piece of what makes Mercury so hostile. The real killers are subtler, more layered, and more total in their destruction. Most people assume Mercury must be the hottest planet in the solar system. It is not. Venus holds that title, thanks to a crushing greenhouse atmosphere. Mercury has almost no atmosphere at all, just a thin, unstable shell of atoms blasted off its surface by the solar wind, technically called an exosphere, which offers 0 thermal protection and 0 pressure. That absence of atmosphere is where everything starts to go wrong. For centuries, astronomers dreamed of standing on other worlds. The age of the telescope gave us maps of Mercury's surface features, craters, ridges, volcanic plains, and the imagination filled in the rest. When we finally sent the Mariner 10 probe in 1974, it confirmed what some suspected. Mercury is a scarred, ancient world, geologically quieter than Earth, pocked with impact craters that have sat undisturbed for billions of years because there is no wind, no rain, no erosion. Nothing to change them. It looks, in many ways, like our moon. And since humans walked on the moon, a part of the human brain asks the natural follow-up question: could we walk on Mercury too? It's worth sitting with that question honestly before dismantling it. We are a species that crossed oceans in wooden boats. We dug through mountains. We learned to fly in under a century of trying, and then within 66 years of the Wright brothers' first flight, we put human beings on another world. The impulse to stand on Mercury, to plant a flag, to look back at the Sun from a distance no human has ever experienced. That impulse is not naive. It is one of the most distinctly human things about us. The problem is that Mercury was not consulted on this dream, and the physics of its surface have no interest in accommodating it. Start with temperature. On Earth, even in the most extreme natural environments, we are dealing with a relatively narrow range. The coldest recorded temperature on Earth's surface is around -89 degrees Celsius. The hottest is around 57 degrees Celsius. Challenging, but survivable with the right gear. Mercury operates on an entirely different scale. Because it rotates extraordinarily slowly, one Mercury day lasts about 59 Earth days. The sunlit side bakes under direct solar radiation for weeks at a time with no atmosphere to distribute that heat. Surface temperatures on the sun-facing side reach 430 degrees Celsius. That is hot enough to melt lead. Hot enough to melt zinc. It is more than 4 times the temperature of a conventional oven set to maximum. No spacesuit material currently in existence or in serious development could insulate a human body from that kind of conductive and radiative heat transfer for more than seconds before structural failure. The suit doesn't just overheat, it begins to break down at the molecular level. Seals warp, visors soften, and the moment any seal fails, you are exposed to vacuum. The shadow side is not a refuge. Temperatures in Mercury's permanently shadowed polar craters drop to around -180 degrees Celsius. In those craters, water ice has been confirmed, frozen for billions of years because sunlight has never touched them. For a human in a suit, shifting from the sunlit side to shadow doesn't provide relief. It means the thermal management system on your suit, already overwhelmed trying to reject heat, suddenly needs to reverse and provide it. No single system can reliably do both at those extremes. The engineering margins simply do not exist. Then there is the radiation. This is where Mercury stops being merely inhospitable and becomes something closer to a biological weapon. Earth's magnetic field and atmosphere act as a radiation shield, deflecting and absorbing solar particles and cosmic rays before they reach ground level. Mercury has a magnetic field. Surprisingly, it does. But it is less than 1% as strong as Earth's, and it is not a smooth, uniform shield. It is fragmented and irregular, creating channels where solar wind particles funnel directly onto the surface rather than being deflected away. On top of that, with no atmospheric column to absorb incoming radiation, the surface receives the full, unfiltered output of a star at close range. The numbers are stark. NASA's radiation exposure limit for career astronauts, a limit set to reduce excess cancer risk to an acceptable level, is around 600 millisieverts over a lifetime. On Mercury's surface, estimates suggest radiation exposure could reach several hundred millisieverts per day in active solar conditions. A lethal whole-body dose, the level at which acute radiation syndrome becomes fatal without immediate medical intervention, is around 4,000 to 5,000 millisieverts received over a short period. On Mercury, during a solar event, you could approach that threshold within days, but you would not need to wait for a solar event to be in serious trouble. Chronic lower-level exposure at Mercury's surface would still be obliterating DNA in your cells at a rate your body's repair mechanisms could not keep pace with. Cells that cannot divide correctly die. Cells that divide incorrectly become something else. The progression from that point is not hypothetical. It is the documented biology of radiation damage, compressed into a timeline measured in days rather than years. Your body, already being cooked or frozen depending on your orientation and suit integrity, is simultaneously being irradiated at the cellular level, but it does not stop there. In the absence of atmospheric pressure, any breach in your suit, a micrometeorite impact, a thermal stress fracture, a seal failure from temperature cycling, means immediate depressurization. Mercury's surface is not protected by an atmosphere, which means micrometeorites that would burn up long before reaching Earth's surface hit Mercury directly. The crater record makes this visible. What it means for a soft-suited human standing on that surface is a constant, unquantifiable statistical threat with no warning and no recovery window. A micrometeorite the size of a grain of sand, traveling at tens of kilometers per second, carries enough kinetic energy to punch through most suit materials designed for current space operations. Even if you set aside the temperature, the radiation, and the impact risk, the gravitational environment compounds your biological deterioration. Mercury's surface gravity is about 38% of Earth's, similar to Mars, lower than the Moon. Extended time in reduced gravity causes accelerated bone density loss, beginning within days. Fluid shifts toward the upper body cause intracranial pressure to rise, compressing the optic nerve, flattening the eyeball, and degrading vision in ways that do not fully reverse when gravity is restored. Muscle tissue begins converting from slow twitch to fast twitch fibers, losing endurance and structural integrity. The cardiovascular system, evolved over millions of years to pump blood upward against Earth's gravity, begins to shrink the heart and redistribute blood volume in ways that cause fainting and organ stress the moment you return to normal gravity. If you return at all. Now stack all of this together. Your suit is failing thermally within minutes of arrival. Your cells are absorbing radiation at catastrophic rates. Every micrometeorite is a silent lottery. Your bones are thinning. Your eyes are changing shape. Your cardiovascular system is restructuring itself. Each of these problems alone is serious. Together, they form a system of cascading failures where solving one does not reduce the pressure from the others. You cannot fix the radiation damage while also managing suit thermal failure. You cannot repair a micrometeorite breach with hands that are losing fine motor control from pressure suit limitations and early radiation effects. The support systems required to address each problem create their own failure points. More power, more weight, more complexity, more things that can go wrong in an environment that punishes every engineering margin you push. This is not a matter of needing better technology, more funding, or more ambitious engineering. With the physics as they are, the proximity to the sun, the absent atmosphere, the radiation environment, the thermal extremes, Mercury is not a planet that permits human surface presence with any technology currently on our roadmap or in our theoretical toolkit. Not difficult, not challenging, prohibited by the same physical laws that govern everything else we know. And yet we have been to Mercury, not with our bodies, but with our minds and our machines. Messenger, the NASA spacecraft launched in 2004, orbited Mercury for 4 years, mapping its surface in extraordinary detail, measuring its magnetic field, confirming the presence of water ice at the poles, and revealing a geologically complex world with a surprisingly large iron core. It told us things about planetary formation, about our solar system's history, that no human expedition could have gathered more efficiently. The Bepi-Colombo mission, a joint ESA and JAXA project launched in 2018, is still en route to Mercury and will expand that picture further. We are learning Mercury's secrets without risking a single human life. There is something humbling in that. We are a species small enough to be killed instantly by the nearest planet to our star, and curious enough to send our machines there anyway. We may never stand on Mercury. The universe did not design it for us. But we looked up, pointed our instruments at a small, scarred world 77 million kilometers closer to the sun, and learned its name. That is not a consolation prize, that is the whole point.